All right, let's go ahead and get started. What should we talk about?
Optimization.
Right. You got a second question?
No, any example problem would be great. And those are probably hard to make up.
Yeah, they are. Did I put one on a quiz or anything recently? I did, right?
Yeah.
This is a good one to talk about. Okay. All right, so yeah, so a lot of people who turned this in had some trouble with it. But even if you nailed it, I think this is a good one to talk about. So I'm building a window out of two pieces of glass, and I'm going to attach them together at that dashed line. So basically, what's the first thing that has to do? Find us the function for the area of the window A in terms of its radius R. So how do you want to start? Or how did you start previously?
You need a function for perimeter, right?
So we need a function for perimeter. And what is that? What do we need that for?
To get one of the variables in terms of another vector.
Okay. So as we've kind of said on some of these other examples, I might not be able to annotate. Hopefully I can. So as we've kind of said in the past, what we really want to do is we're going to optimize something. And in this case, what are we trying to optimize? Area. Trying to optimize area, right? And in fact, it's kind of left vague right now. Are we trying to minimize it or maximize it? We're trying to find one of those two extremes. Mm-hmm. So from there, that's our goal. That's what we're trying to optimize. The other thing we need to talk about is, what's our constraint? What's the thing that's going to limit us in that goal?
The perimeter of the window is 8 meters.
So we know the perimeter of the window is 8 meters. So basically what Solomon is getting at is, basically setting up a problem around this constraint. Mm-hmm. All right, so how do we find the perimeter of this thing?
You have to set up the equation first.
Okay. So how do we do that?
A equals 2.
So there's nobody on Zoom, so I'll just support. So our perimeter is going to be equal to 8, right? Mm-hmm. So in this specific instance, can we represent the perimeter in terms of, the symbols that are up there, the measurements that are up there?
2R plus 2H.
2R, so where's the 2R come from?
That's just the length of the long side.
Okay, so perimeter equals 2R plus 2H.
I forgot that it's half of the perimeter of the circle.
So yeah, so 2R comes from the base, so we're at the very bottom segment.
Right.
The 2H comes from the two side walls, right? And then we have to have that semicircular arc, which will be pi r plus pi r. Okay, so here's our perimeter. It's a function right now of two variables. Is that okay?
Well, no, because you have to get it R.
Got to get it in terms of. Actually, we want to find area in terms of R, right?
Yes.
Okay, so what else we know? So this right here is our constraint, this perimeter thing. And we said before we're trying to optimize The area?
Mhm.
So let's do this first. Let's come up with the area as a function of R and H. And then from there, I think we'll have enough information to get it down to a single variable. So how do I find the area of this thing?
2RH,
Okay, where does that come from?
that comes from the base and the height.
Okay, so the rectangular part will have an area of 2RH plus what?
Plus pi r squared over 2.
Plus the area of half a circle. So
Yeah.
1/2 pi r squared. So I think that's good. And one thing we kind of skipped because I sort of given to you, but really take stock of what the variables are that you have to deal with. In this case, you know, the radius of the semicircular bit is R and the height of the rectangular portion is H. So those things are kind of given to you, but typically you'll have to, you know, make sure you have a handle on what those things actually are. All right, so I got my constraint equation, I got my goal, my thing I want to optimize. Where do I go from here?
You would solve for H,
Solve which one for H?
perimeter, because you know that's equal to 8.
All right, so that's the only one I know that has a value. So let's do that. So we got 2R plus 2H plus pi R equals 8. And we're solving for what?
For H.
For H. So 2H equals 8 minus 2R minus pi R. H equals 8 minus 2R minus pi R over 2. Or I'm going to go this way. 4 minus R minus pi R over 2. All right, any questions there? Why did I do that?
Get H in terms of R.
H in terms of R.
And then now you can sub in
Now you
that.
can sub in that, yeah,
Right.
for H.
So part A of this is to find. Part A is to find an area function that only depends upon R. So now I can do that. So the area depending on R is 2R times.
4 minus R minus pi.
Actually, I just realized that I might as well leave that all over 2. So 2R times 8 minus 2R minus pi R all over 2 plus 1/2 pi R squared. Cancel, cancel. So area as a function of R is equal to 8R minus 2R squared minus pi R squared plus 1/2 pi R squared. One pair of like terms cancels or combines. 8R minus 2R squared minus 1/2 pi R squared. So that was kind of a lot. So let's pause and reflect on what we need to. So got our constraints, figure out the thing we want to optimize. Still don't know which way we want to optimize it, but that's the thing that we want to find an extreme value of. We got an equation, so that optimization function, we got it in terms of 2 variables and then distilled it into only a single variable. Right, any questions about how that all shook out so far? Okay, so I think that's good for A. Now what?
Now we find the derivative in terms of R.
Okay, I want to find a derivative. What tells you I want to find a derivative?
Optimize.
So if you want to optimize, you need a derivative. Why? What specifically is the derivative going to get us to?
When you set it equal to 0, that'll find you either a minimum or a maximum.
Right. It'll find you critical points, which
Yeah.
might be where extreme values are.
What does a critical value of R mean, like in the context of this problem? Like
So what does the critical value of a function mean?
when the derivative rate changes 0.
Yeah, when the derivative equals 0, right?
But like,
So
what does that mean? Like, is it just
basically, so the critical value of R does not make sense outside the context of part A.
okay?
So the critical value of R really comes from the fact that we have an area function that is governed by R.
But it's completely unrelated. It's like the actual shape or like circle. Like
No, it's not. So It's completely related because this function only makes sense for that thing, right?
Yeah.
So basically what we did in all of part A is we reduced this physical object into this mathematical equation. So yeah, we're still dealing with that. We just are doing it with this in this language.
Okay.
But yeah, they're all still related. We're just basically, we made a model for a physical thing.
And with the derivative, we'll be able to find either the smallest version of that or the largest.
Right. So yeah, setting it equal to 0 is an effort to find what that critical value is of R. So 8 equals 4R plus pi R. 8 equals R times 4 plus pi. So R equals 8 over 4 plus pi. And I believe that's B. So that value is a critical value because for that value of R, the area is neither growing nor shrinking. So that's B. Any questions on how we figured out that critical value of R? Based on the quizzes I saw, I mean, most people who had a hard time with this, it wasn't the algebra that got them, at least not the algebra. So basically, I had very few people who successfully got this thing and then missed this thing. And I think, I hope you'll agree with me that that's true of most of these optimization problems is building this function is probably the most difficult and the most important part of the whole thing. Which is not to say that easy things follow it, but I believe this is the majority of the battle. So this is your data review. If we got to talk about any more of this, let's talk about it either right now or when we get done. Are we happy with our R value? Are we happy with how we got to it? Okay, so I'm still not satisfied that it's a maximum or minimum, so what should we do? Left and right. You can do the left and right thing. If you want to do that, it probably makes sense to know what this thing is, approximately. So I think it was like 1.12 or something. What important is that it's somewhere between 1 and 2. So yeah, we can do the left or right thing. I'm going to work really out of order. So I know that, let's say R is equal to 1.12. Which means if I want to look at what the area is doing, I'm going to look at A prime, knowing that 1.12 is critical value. And I'll use, what other value should I use?
0.
I think in this case, I would not want to use 0.
So 1.
Yeah, we'll use 1 just because I think this makes no sense if R is equal to 0, right?
Yeah.
So let's use 1 and we'll use 2.
Because you can't have a 0 area.
If you have R equals 0, I think you have no window, which means the perimeter could not equal 8. So for R equals 1, A prime of 1 is equal to, where is it? 8 minus 4 minus pi, which is, I think I can safely say that's positive, right? Pi is not as big as 4.
Yeah.
So I think that's positive. Hopefully the other one's negative. So A prime of 2 is equal to 8 minus 8 minus 2 pi. So what have I really found?
Maximum.
I found a maximum area. I didn't see anyone do this on the quiz, but one thing I want to remind you of, just because sometimes it's convenient, is the second derivative can also tell you this information.
Yeah.
So what is the second derivative of A with respect to R? It is, negative 4 minus pi. That's a constant, right? It's a negative constant.
Yep.
Which means, basically what we found is this, at the critical value, so we're the rate of change of area with respect to radius is 0. The rate of change of area is 0, but the rate of change of that rate of change is negative, which means that has to be a maximum. The slope is 0 and the slope is decreasing. If you're not happy with that, and it seems like many of you, if not all of you, are more comfortable with this thing here.
Well, yeah, because essentially if the second derivative is 0 or negative, that means that it's concave down, which means
Right.
it's maximum.
Also, the second derivative is constant, which means, and it's okay if you don't realize this, but it means you're looking at a parabola. And parabolas are either opening down or opening up. But yeah, if you're happy with this, like I said, most of you are comfortable with this scheme here where you're basically testing the derivative in a couple of other places. That's fine. But yeah, knowing what the second derivative says about a function is also valuable. But either way you get to that minimum or maximum, you're good. So we found out that area was a maximum. Anything else about that? All right, what else? Yeah.
I have a quick question about the last night's homework. On the second problem, like the first part, where it was
Okay.
saying take the derivative from, or not, use like the beginning values
Mhm.
of the velocity to find it.
Yeah.
I don't know what that meant. I was able to find the second one.
Okay. So
I just don't know what, like, I tried doing left and right and that didn't work, but.
yeah, the beginning of the interval should have been
Should have been left.
the left end.
Yeah.
So let me. This is last night's homework.
Yeah, it was the second problem.
5-1.
5-1.
5-1 question.
Question 2 was the first one.
Well, yeah, I had trouble with that one too. I
Okay.
just added wrong.
I did it with one including 0 and then one without including 0, and maybe I did the math one, but I got the same answer.
Okay. Am I sharing this? I don't think I am. Yeah, now. Okay. So. We can do this both ways, I think. So we're trying to estimate the distance, and all you know is what the speed was at these like 12-second timestamps. And Isabel, the one you're having trouble with was the first part?
Yeah, it was part A.
Okay. Estimate the distance in feet traveled by the motorcycle during the time interval from 0 to 60 seconds using the velocities at the beginning of the time intervals. So essentially what I'm doing here, I'm taking a Riemann sum, right? Starting with number 1, how many intervals or how many rectangles am I dealing with?
5.
Ooh, that's a problem.
No, there's 5.
5's not 48. Start with one.
So how many speed values did I give you?
There's 6.
There are 6 there, right? Does that mean 6 rectangles? No. Hopefully this convinces you. I'm trying to find the distance over what period of time?
60 seconds, 1 minute.
A minute, right? So I'm trying to find the distance traveled in 60 seconds, right? I only know about this. So for that, I need speed and time. But I only know speeds over how big of it, what size intervals do I know the speed for? 12 seconds, right? So how many of those do I need?
5.
I need 5. So yeah, five time intervals that are each 12 seconds long is what I need. So I'm setting up this, this Riemann sum. I'm going to basically find this V, and I'll call it V sub I. I shouldn't call it D. Let's just start the whole thing over. VI delta T. And I'll call it VI star because really we're going to sample these at different places for different parts of this question. Does that make sense what that Riemann sum is? So for the left-hand side, let's just start writing these things out. What is V1 star? So basically, the first interval goes between, basically, is the 12-second span from time equals 0 to time equals 12, right? So that's a 12-second interval, just like they're all going to be. But what speed do I care about for that first interval?
23,
Why 23?
because that's the left side.
That's the left interval, or what's the language they used? That's the beginning of the time interval, right? Which, yeah, graphically speaking, would be the left. And then from there, so I think, are we okay with the idea of me taking this shortcut? We're taking 5 intervals and they're all equally, they all have an equal time width, right?
Yes.
Okay. Anybody? Okay, at any time, stop me. I'm only hearing a couple of voices, so please stop me if you need. What are the rest of these speeds going to be? 21 feet per second.
28.
The next one's 28. And then after 28, 29 feet per second, and then 28. So that's sum right there. Should give you the distance. And I'm more interested in the fact that we understand where that comes from. Actually spitting out that number, but we okay with that sum?
Why did the last 23 go?
By the last one, what?
Like the last 23 of the.
Yeah, did I miss 23?
Yes.
Should I have?
Yes.
Okay. So let me draw a graph here of essentially what we're looking at. So how many speed values and time values do I have? So 0, 12, 24, 36, 48, and 60. And then basically what I have is, let me try to represent this somewhat accurately. Basically what I have is this. I don't really know what I have. Actually, I think I've already prejudiced this by making the intervals the height that I did. Oh wait, no, I didn't. Those are those times. 30s. Actually, I didn't want to do that. Let's just think about this symbolically. So how many rectangles am I going to make? 5. And all I know right now is that they're going to have these widths. Erasing is too hard over Zoom, so actually, let's stop being lazy about it. Okay. So I know the speed at those 6 points, right? But over the first interval from 0 to 12 seconds, for example, what's the speed? Is there a single speed that is taking over that? So I have to choose one, right? So the first question is basically telling you choose whatever it starts with.
Yeah. So use the left word. So.
Right. So here's the thing. I am choosing that value, and I'm going to act as if the motorcycle, the motorcycle is traveling at whatever speed it was traveling at time equals 0 for the entire 12-second span. And then I'm going to repeat that process for the other 4 subintervals. But notice, because of that, let's call this TI. What are the time values that I'm sampling if I'm using the left-hand points of the left-hand points of each interval?
All of which have 16.
So let's list them. There are not that many of them, right?
12, 0, 5, 0, 0,
And is that the complete list?
yeah.
Okay. So because of that, I am leaving off 60. Because another way to think about it is this: if I'm taking the left-hand points of the intervals, then if I sample at t equals 60, then I'm saying, all right, what happens for 12 seconds after that, which is something I had no idea about. So, a couple ways to look at it. If you're sampling the left-hand points of all your intervals, then your intervals are between 0 and 12, 12 and 24, 24 and 36, 36 and 48, and 48 and 60. So sampling at 60 is, there's no interval that it's associated with if you're looking beyond 60. And that's another reason to pay attention to what the time bases are, because if you kind of just go into like autopilot, it's really easy to just, all right, just multiply 12 by all those numbers down. And if you do that, you're basically working with too much information. Any more questions about this thing? Riemann sums? Okay. What else?
Maybe one definite interval.
A definite interval?
Yeah.
You got one? Those are a little easier to cook up in the fly.
Yeah, I liked the, or yeah, it's just another, number one on, woodwork 5.1.
Okay, what was it?
Oh, wait, no, never mind, that's the wrong thing, never mind. Definitely. Oh, yeah, yeah, that's.
Is this what comments you're asking? How to do things like this?
Yes.
Okay. All right, what do we do? Do you want me to find this exactly, or do you want to approximate it with a Riemann sum? Like what?
No, like an exact value.
You want an exact? Okay. All right, cool. So we want to find this exactly. So how should we start looking at that?
A Riemann sum would just be like 2 to 7, like it would just, the delta x would just be 1, and then you just plug in 2 through 7.
Oh, that's one way to do it.
Yeah.
If I said I wanted 5 rectangles that were all one wide, but I could also say I wanted a Riemann sum with 25 rectangles. I mean, there's an infinite number of ways to define those.
Okay.
But if you want to find the exact value, then you're looking at an integral.
Mhm.
Which if you're gonna, right now, the only way we all can get to integrals is through, oh, you have 2 ways. One is if you can figure out an area of that thing exactly, like through geometry, that'll get you there, or we can set it up as an infinite Riemann sum. Your choice. In fact, maybe it's worthwhile to do both. Let's do the infinite Riemann sum first. So I'll get you started. Basically, if we're going to set this up as an infinite Riemann sum, and what I mean by that is a Riemann sum with infinitely many rectangles, that's equal to this, as the limit as n approaches infinity of this sum, I equals 1 to n of f of xi star times delta x. So now we got to figure out what all these pieces are. Isabel?
The f of x is going to be our function that's on the inside, so the x plus 3,
Okay.
and our intervals are from x equals 2 to x equals 7.
Mm-hmm. So yeah, the full interval is from 2 to 7. So let's start there actually. I mean, we got the function. But we know that the full interval is from 2 to 7. Is there anything about the Riemann sum that we can figure out based on that?
Is I not equal to 2?
I will be equal to every integer from 1 all the way up to n. So I is a variable. So basically, the goals here are this. We want to replace this thing, this f of x sub I star, with some expression that's in terms of I. And you also want to replace delta x with something. Isabel,
Is delta x the 7 minus 2 over n?
how'd you get that?
Because delta x is like each, it's the difference of, it's the width of each individual square, it's a rectangle.
Mhm.
And since we don't know how many we have, we don't know the final like result, so we divide it by how many.
Right. So I think this might be the first time I've thrown one at you where the interval didn't start at 0, which is fine. But the width of the whole thing is 5, and I'm going to split it up into n equal chunks. Each one's going to be 5 over n. So that allows us to, let's just drop things in as we find them. We know that delta x is equal to 5 over n. Now we got to figure out how to represent f of xi star in terms of i's and n's. So here's my advice in general: find the first few x values, and then hopefully from there you can figure out what x would be for any I value. So you want to do a left sum, you want to do a right sum, what are you feeling like? Left sounds good. Left makes it start easier. So basically this is my function, right? And I care about it from 2 to 7. I'm trying to find this area. So if we're doing left endpoints, what is our first x value going to be? 2. So our first value, x1 is 2. What's our next one? What is x sub 2? Nope. You're going all the way across.
Oh,
So remember, we split up this 2, 7 interval into all these pieces, right? So the first interval begins at 2. Or the first rectangle has its left side at 2. The next rectangle is going to have its left endpoint, or left endpoint width. Or another way to ask that is, how far over am I moving from 2? Not 1, not n. 5 over n, right? That's the whole beauty of delta x. The delta x tells me how far apart each of my endpoints, or each one of my sample points is. So what is x sub 2?
is this all right?
No. How'd you get 10 over n?
I multiplied 5 over n by the first.
Yeah, we don't want to multiply them together. So x, like think of x equals 2 like as a position. You're adding that. So we're adding that change in x. So 2 plus 5 over n. What's the next one? Isabel?
Clarify question, for the multiplication, would that be if you divided that section just into 2 squares and that's it? If you like multiplied it by 4 instead?
I'm actually not sure what that multiplication would get you, because the fact that we're starting this interval at a place other than 0, it forces us to be a little more careful about how we set these things up. So Garrett is offering this about the next point. Do we agree with that?
Yeah.
Starting at 2, to get to the next one, I add 5 in. To get to the next one, I add 5 in to get 5 over, not 5 in, 5 over in. So, see the pattern emerging?
Yes.
Okay. So unlike the previous examples we did where the intervals all started at 0, in this one, you have that constant 2 every time, right? But hopefully we're seeing the pattern that emerges on top of that. So should we do a couple more, or can I jump ahead to xi?
Is it,
It's 2 plus 2 plus 5.
2 plus 5 I over n? Are you sure?
Yep.
It's a little bit off, because you all decided to go left this time, right? So it's actually going to be 5i minus 1 over n. And look at the two middle values here. This is 5 times 1 over n, right? This is 5 times 2 over n, and these indices are 2 and 3. So I think you're kind of trading it off, like the left versus right sum. Basically, where do you want to introduce the complications, now or later? And I think, yeah, Garrett kind of fell into the same trap that you all did, and I'm sure I did 100 times before I learned to avoid it. So we have x sub I general now, right?
Yes.
That's an important thing. Doesn't look like an I. Now it does. That's xi. I really want f of xi. So how am I going to get that?
you plug that in for x,
Plug that in for x into what?
into the original x plus 2.
Okay. So f of xi is going to be equal to 2 plus 5 times I minus 1 over n plus 3, right? Which is 5 plus 5i minus 1 all over n. So now I think we have the full Riemann sum that I think we're ready to deal with. And it's going to be gross, but that's okay. 5 plus 5 times I minus 1 all over n times 5n. You okay with that? Man, I think we should do some simplifying, but are we okay with what it looks like right now?
Yeah.
Here it tells me, would a midpoint be 2 plus 5 times I minus 0.5 over? I think that would work.
Does it matter if you use midpoints, left points, right
No,
points?
because we're going, how many rectangles are we going to have? So in this case, no, because the thing we're going to find is going to be exact. It only matters where you take the endpoints if you're going to do an approximation. But this is going to be, when we're done, we're going to have something exactly correct. So the limit as n approaches infinity of, let's just expand all the brackets to see where we end up. First, we'll do the inside. 5 plus 5i over n minus 5 over n, all times 5 over n. I hope I have enough room to do this. (25 over n plus 25i over n.
It's not an I squared, right?
I don't have an I squared, I shouldn't.
Okay.
Minus 25 over n squared. Is that all of it? Okay. Can I work with this thing now? I have 3 terms, right? How many of them are variable?
That's I.
Just the middle one, right? Because it has the I.
Yeah.
So here's what I can do now to make it really clear. And I want to make this known. It'd be really dirty if I asked you something this involved in a test, but I think it's good for us to look at. So you have an idea of like how all this notation actually plays out. So 25 over n plus this sum. Is anybody going to tell on me if I don't add all the indices on these? All right. Let's deal with the first and last one first, because they don't even involve the I. What is this sum going to be? The sum from I equals 1 to n of 25 over n. Does 25 over n vary? No. So it's a constant, right? So it's just 25 plus n plus 25 plus n plus 20. How many times?
10 times.
So what's that all add up to? It's 25 over n times n, right?
Oh, that's a little one.
It's just 20. So equals 25. How about the one on the far right? I have 25 over n squared times n. And that comes out to 25 over n. And then this thing here, here's what I'm going to do. I'm going to factor out the 25 over n. And in the interest of time, I'm going to fast forward a little bit and tell you this comes out to 25 plus 25 over 2, which is 37.5, I think.
So why do you multiply it by n, like to, on that, this step before what we just did?
Okay, so let's think about it in terms of rectangles. Actually, is that the right way to think of this? Let's think about it in terms of what it is. It's a sum, right? So for this one here, I am adding, so this 25 over n is a constant, right? And the summation, this sigma means I'm going to add a bunch of them together. 25 over n plus 25 over n plus 25 over n. How many of those 25 over n's am I going to add together? N, because of what? How do you know that?
The multiplication.
But how do you know there are n of those things?
Oh, the summation, sorry. Tells us that.
That's what that's what this defines, right? So yeah, I'm going to add up 25 over n times.
Which means it's the same.
So it's 25 over n times n, right? Which is why that comes out to a constant. So
When we have like summation, I know that you said we might not ask for something that's detailed on the test, but should we typically take that evaluation like step every time we do something like this?
what do you mean the evaluation
Or
step?
like this step right now, we're making like n times instead of just like.
How, whatever it is, whatever helps you think about what that summation is doing. I mean, you all are at the point where I think, I don't think it's obvious to you that this thing right here of itself equals 25. Nor should it. So, yeah, ask yourself, all right, I'm going to add a bunch of these things together. And if it helps you write out the first few terms, 25 over n plus 25 over n. And if you do it right, it'll probably jump out at you right away. It's like, oh, nothing's varied. I can just multiply that by how many of them there are. But right now, the sigma notation is a weird thing for, you know, especially when you're used to, where you're first seeing it. Whatever you need to do to organize it is great. Jared?
You said we could then also do this problem in terms of area.
Yeah, in fact, I got a picture here, right?
Yeah.
In fact, I'm not going to try to clutter this new thing anymore. Let me get a new page. So our area was between x equals 2 and x equals 7, right?
Mhm.
Our function is something like that.
Yep.
What shape am I making? So we can find this using an area, right?
Oh, yeah.
But we better know what shape we're looking at, so we can rely on our good old geometry tools. What's the name of that geometric shape there? Or if you can't think of what that is, can I break it down into simple things?
Just a triangle.
I have a triangle and a rectangle, right? What's the area of this rectangle?
5 times,
What's that 5? Where'd you get that 5 from?
the distance from the
Yeah, the
beginning to
base.
the edge.
So that's the width, right? Gotta know how tall it is. How tall is that rectangle?
Why not to X?
And just to remind you, this function is x plus 3.
So,
So this point right here is what?
so 5, and the second one is 10.
5, 5, and 7, 10, right? So what is the height of that rectangle? Also 5, right? So that should be.
Square.
Is this square? Is that, yeah, I mean, I didn't promise that my drawing was accurate. It's just, it just helps us organize what we're doing. So yeah, it's a square. And then the area of the triangle is what? 1/2 times something times something. So what's the base?
5
Better also be 5.
times 5, yeah.
Wait, why is the point, wouldn't the point be 2-5, not 5-5?
Yeah, absolutely.
Oh, shit.
Yeah, it absolutely is. So yeah, 2, 5, and 7, 10. That's the same number we got before, right?
Yeah.
And I think it'll become more clear next week when we get into actually like dealing with integrals, not thinking about it in terms of Riemann sums, but in this Riemann sum, I also got 25 plus 12.5, like those specific things added together.
So if it's an equation that simple, depending on what the shape looks like.
Yeah, I mean, so if I give you something that you can just think of as an area, do that. If I give you a parabola, you have no real hope of making that work.
Yeah.
I don't even know what those shapes are called where you have the area under your parabola. I don't know if there is a name for it, but right now, those are not things you can do using areas. You have to use, actual integration. Any questions here? All right. Any last minute things? We got about 3 minutes left, so I don't know how deep I can dive into something, but what do you want to talk about? All right. One thing I want to say, and I will put it, I'll make an announcement on Canvas about this. So test Monday, right?
Yeah.
Wednesday, I will be out of town. I cannot be here. So the reason I bring that up is because I'm hoping that since there are only like 8 or 9 people here, that most people catch the recording or join me on Zoom. I can't promise that will be available to you. So, yeah, if you're on the fence about being here in person on Wednesday, I would do it just because I can't promise you I'll have something recorded to share with you. I'll post what I did last semester, but it might not be.
So you're saying don't come to class on Zoom?
Oh, you don't, dude. We're having class. I won't be teaching it, but somebody will.
Okay.
Okay, yeah, sorry, I was confusing. I have a sub on Wednesday.
Okay, cool.
Be here. I won't be, but you should be. I just can't promise you there'll be a Zoom recording that he'll generate. All right. Have a good weekend, everybody.
You too. Happy early